Right, so today we'll talk about virtual threads and their relation to scalability, how they can help you or harm you if you don't know how to use them properly. Just briefly about me, my name is Jakub. I work for over 20 years, mostly in Java. I'm originally a C developer converted to Java. I did some Golang, but if I need to implement something, I usually pick Java because I know it the best. I have I also have a lot of experience in DevOps space. I help 4 different companies to convert from VMs to containers and Kubernetes and other stuff. I developed like 4 different CI/CD systems. I mostly worked in e-commerce. My very first commercial experience was Czech Computer, which went off the business last month, I guess. So if you ever bought something on Czech Computer, you probably hit some of my codes. I spent quite some time in Fortuna, sport betting company. So if you're placing any bets for sports, then you're probably hitting most of the systems that I did. And now I work for Sky, where I work in global streaming technology. We create backends for multiple streaming companies. I think the only one available in Czech Republic is Sky Showtime. A lot of stuff for kids, can recommend. But the biggest offering is probably Peacock, which is in the United States. For Peacock, it's quite a challenge. Very often we are streaming a live match. You can imagine when the live match starts, a lot of people, in our case, it's millions of people, start a TV. The TVs usually don't have access token valid anymore, so they come with the refresh token, and then that's when they hit our REST APIs. And that's where we need to be able to scale well enough. And that's exactly where virtual threads may eventually come in play. So today we'll just briefly talk about platform threads because it's important to understand like the old stuff. Then we'll talk about virtual threads, how they work, what's the magic behind them, what are some issues and limitations that current implementation has, when you should use them, and where it will probably lead in the very short future, hopefully. So platform threads. When you start a thread in Java, it will allocate some amount of memory, and the amount of memory that is allocated for stack is limited. So typically, on my system, if I don't change anything, it takes 2 megabytes. You can change it with this parameter, actually. So there's only a limited amount of threads in the old world that you can create, and if you keep creating them on and on forever, you will eventually run out of memory. I try to implement a very simple piece of code. The second line can be replaced by just a plain old constructor. You could create a new thread. What's important part is that it waits for a very long amount of time, and we just keep count of them. So if we run this code on my machine, which is a regular MacBook Pro, I managed to create 9,000 something threads before I ran out of memory. And you need to keep in mind that that's not the only memory that you'll be consuming. There's the rest of the application is just the threads that you are creating. So it's kind of tricky to create many of them. And as you probably know, most of the servlet containers have a connection pool, which is backed by some thread pool. So one of the first things that you'll be doing when you're fine-tuning performance of your application will be probably fine-tuning the amount of threads in that pool. Of course, you can do fancy stuff like replace it by non-blocking I/O and other things, but these things tend to be rather complicated. It's where virtual threads came as an idea to the smart heads of Oracle developers that develop Java. So they've been added to Java 21 as a final version, although they were in a preview in quite a few previous of them. I actually used them in production since Java 20 in my previous company, not in Sky. They are intended to be lightweight threads. They should not be like, you should not think about them as of a regular thread. It should be a thread that does some task and then it just dies and goes away. Actually, pooling virtual threads is an anti-pattern and it should be avoided. So if you will just take your regular thread pool right now and you will replace it by the virtual threads, you will see some performances because it's not what it's meant to be used like. So you can think of it as a thread per request, per task, or per connection. The goal of that was to have a more simpler readable code that is like understandable, because when you try to, have you ever someone tried to implement something reactive like with the, yeah, it's a pain because it's not a procedural code. You're basically building pipes that may eventually have something flowing in them. And if you go back to the code after a year, I have no idea what the code does anymore. So that's where it comes in. The aim was to create more than 1 million connections on a commodity hardware so that you can handle all this stuff. So the more you can handle with a single container, then you can get rid of stuff like configuring autoscalers and other stuff that is like quite boring and more for the DevOps stuff. And it should hopefully obviate the need for this reactive code that everybody hates, but it's so fancy that we all tried and probably failed, most of us, at least I did, to get it right. I mean, it worked, but I didn't like it. So what's the magic behind it? Well, virtual thread is basically a wrapper on top of a continuation. Continuation is a very simple coding construct. It's just another name for a same, I mean, it comes from the programming language theory, and the same name could be like fiber, coroutine, or anything else. They've decided to go with continuations. The reason why it's just a wrapper is because Java engineers like to keep things backwards compatible. So it's built on top of the threading API, the good old one, but they needed to do some smart stuff, so they buried continuation inside. It's not supposed to be used directly, although you can do that. What's the important part? Continuation is just a piece of code, just like a regular runnable. You can do whatever you want inside there, but it has a support for yield. When a continuation yields, it basically gives up its execution, and you can continue it later. So how can you imagine it? It looks complicated, but it's not. Each continuation takes a scope. It's just a fancy name. You can like use it for some complicated stuff that's not part of today's talk. And there's a runnable. In this case, there's a simple runnable that prints out let's count, prints number 1, and then it will stop execution because it yields. When we run it the second time, it will print number 2, and then it yields again. And since we are not running it the third time and the main will end, the whole continuation will basically be deleted. The program ends, and number 3 will not be printed ever. So an output, that was quite big, right? As we can see, the output is just 1, 2, and 3 was never executed because we never called the third run. So it yielded and it never was continued, which is nice. What the engineers in Oracle did, they went to all the different places when the threads are currently blocking. They've put in conditions, and if you are running a virtual thread, then they actually unwrap the continuation and they yield it so that it gives up static execution, and it frees some space for other virtual threads to be executed, which is like the way how they effectively can use the hardware. So how exactly does it work with the memory? Well, you have a main function that does something in continuation. Basically, once you run continuation run, you do something. In our case, it was the print of the regular number on the output, and then you yield. What happens when you yield? The platform takes the continuation and it copies it from the stack to the heap, freeing space in stack for the others, and it just resumes the execution of whatever code was next. Same happens when you resume the continuation. It's taken from a heap, it's copied back to the stack, and then the execution is resumed to the whatever was the last yield that was inside that function. So this way, you can imagine that it uses the stack much more effectively. So if you run the very same code, but this time there's this important change of starting actually virtual threads, but the inside is pretty much the same, we can get a very different result than previously 9,000. So this execution was kept for 256 megabytes of RAM, and we managed to create 300,000 threads. I ran it once more with 1 gigabyte of RAM, and it was 1.5 million threads. And the top that I got on my machine was 17 million. But yeah, I mean, it's a stupid demo, but it's a completely different scale that you can have. So if you would replace the regular connection pool with virtual connection pool, which will basically create a new virtual thread for each request, then you will get rid of an issue of scaling that thread pool, because then it will just scale to whatever extent it can, because there's always a limit. So most important part about virtual threads is how they actually work. So the important term here is mounting. So when you are creating virtual threads, they are being submitted to a virtual thread scheduler. And it's nothing else than the regular good old fork join. By default, it allocates, I think it's double the amount of cores available in the system, and the size of this fork join pool is kept there's a hard cap of 256, at least last time I checked. So what essentially happens when a virtual thread is scheduled and it's lucky enough that there's a free platform thread available, it is mounted on top of that platform thread, which is the regular operating system thread. And then it actually executes, because unless it's mounted, it doesn't do anything, because it can't, because there's no execution that can be done. So essentially, the performance of this fork join pool kind of influences how good or bad the performance of that stuff is. So I would expect in the future some improvements in this space. And then there's also the pinning. Pinning is a horrible thing that is a current limitation of the threads. So now that we know how the threads actually work, then we should check how they actually work, but the way they are broken. So pinning happens when a piece of code inside virtual thread enters a synchronized block and does something blocking. The reason behind it is fairly simple. It's because how the hotspot VM implements monitors. Because when a monitor logs in hotspot VM, the hotspot binds the log to an ID of a thread. And since the virtual thread is actually the platform thread, it will bind it to the platform thread. And if you would not pin that virtual thread to that platform thread, then it would know that it's the log of that thread, and it would be a mess because the logs would stop working. So what effectively can happen, if all the threads are effectively being pinned, then all the others will just keep waiting for the new ones. And until the operation that got the stuff pinned unblocks, then it will effectively not do anything. This is one of the reasons why I've heard people that, yeah, we switched to virtual threads, but it was horrible because the performance went down and it was miserable and we didn't see any benefit of it. Yeah, well, that's because they were using it wrong. There are quite a few things that you can do to avoid it, but it's not avoidable completely. And the worst part is that you don't even know that it happens, because the only way how you can detect it, that you either enable a parameter on the JDK level, which it has two options, it's short or full, but it will just print out in the log, and it's not very useful, right? So the other option you have, you can hook in this event, which is a Java flight recorder event. Then you can actually do something useful, like use a micrometer, expose it on the Prometheus, and get an alert that it actually is happening, and you should be aware of the code. Right now, there's not much you can do about it. If you know that it happens, then you can change the code, which is actually running inside virtual threads, and do something about it. But yeah, it's probably a subject of change in the future. And the bad part is also thread local. As you probably know, for example, in Spring Boot or in Spring MVC, when you are processing a request, it creates a lot of thread locals. One of them is holding, for example, a request context. If you're using Spring Security, it's holding also the Spring Security context. And imagine that instead of having 9,000 threads, you suddenly have 1.5 million threads, and each of them is holding request context, and it's a massive amount of memory, and you will very quickly run out of memory eventually. So that's one thing that you should keep in mind, that they should be rather avoided. I mean, in some cases you can't really avoid it, but still. An alternative is code values. The best part about code values is that they have a better way of sharing, because they have a scope context that might be easily shared among different threads. But the best part is probably the automatic cleanup, because thread locals, you work with them, I guess. You need to clean them up manually. These code values will be cleaned up automatically, and it's much better. And they are implemented in a different manner, because have you ever checked how the thread local is implemented? Because there's just a thread local map which holds like an ID of a thread, and then the thread local, which may grow like eventually to a really large amount of threads with millions of virtual threads. So that's probably the two biggest issues with virtual threads. Other common mistakes, well, in general, the bottom line is not understanding where the performance benefit comes from. It's in the numbers, it's not in the performance, because at the end of the day, it's still the good old thread. It's just using the CPU more effectively. People do all the stupid things like replacing them by virtual threads and expecting that something will change, or doing like some heavy crunching of numbers inside the virtual thread, which will effectively just use the platform thread, and it will not be available to any other threads and other stuff. So when you try to migrate, just keep that thing as simple as possible. That thing will eventually die. You don't need to take care of it because the platform will do that for you, all the heavy lifting. Migrate tasks to virtual threads, not threads that you are using. If you're still using some heavy computation, just keep it in the good old thread pool because it won't help you anyhow. To avoid the limitation of pinning, people use semaphores instead of the synchronized blocks, but you can't really avoid it because, for example, even if you call some operation on top of a concurrent hash map, these operations, some of them are synchronized. So you may not even know that you are calling a blocking operation inside synchronized block, and it will happen. So I would strongly recommend to be aware that you are actually pinning something because you'll be really surprised that it happens. And this stuff will be much better soon, hopefully. Best scenarios is when you are handling high concurrency scenario. Handling requests in REST APIs is exactly the part where once the pinning issue is solved, we will see a massive increase in the amount of stuff that we can do with a single container with not that much of a CPU. It's really good with IO-bound operation because, like I said, whenever they do some IO operation, they yield and another thread can do it whatever it needs to do and it's runnable. So it's more effective to use the CPU that way. Don't use it for the CPU intensive tasks because that's not what it's well suited for, because if you're crunching numbers or rendering some stuff or whatnot, it won't help you because there won't be any benefit because the numbers are not helping because there's still just a regular amount of threads that you can run on that particular CPU at the same time. In the future, we can expect some improvements in IO events. Recently, they did some experiments. I recommend there's a very good YouTube video called Virtual Threads What's Next that talks about this a bit more. They significantly improve the performance in Java 24, and hopefully they will make it to Java 25 to the long-term support release, because at the end of the day, we are only allowed to use long-term supported stuff, right? So until Java 25, I would not recommend using it because there's way too many things that you need to keep in mind when using it. We'll probably see some improvements in the structured concurrency space that will probably allow us, it basically allows you to run multiple things and decide on what happens if one of the threads fails, for example, or to combine like multiple results and such stuff. So eventually, I believe that reactive programming might be replaced by this simple stuff that will be simple to read, simple to understand, and it will scale just because the platform allows it to scale. And the most important JEP, which I believe was merged just last week to the Java 24 early access, is this one, which basically is the implementation that got rid of pinning completely. They did some smart hacks that they actually explain in that What's Next video. I strongly recommend that one. Anyways, hopefully in the next long-term support release, it will just work without any issues, because if it wasn't for pinning, it would be probably quite okay. That's it.
Okay, questions? Oh, perfect.
Do you really think that parallel programming is simple enough to substitute programmer with compiler?
Yeah, well, that depends.
It is what we are talking about, right?
Yeah, well, I wouldn't say it's that easy, but yeah, it's making things simpler, but that still doesn't mean that you don't need to understand how it works. And I would say that the reactive programming was so difficult that only the senior people that I worked with were like capable of developing anything useful in that. And whenever some junior came and saw the reactive stuff, they said like, I'm not touching this, because they had no idea what they're doing. Or they did super complicated stuff. They went all the way through the like repository, service layer, control layer, and then they called the blocking operation because they were wrapping it in a pageable, for example.
Yeah, I agree. Mono web flags style reactive programming is a hell, but we have coroutines in some other languages, right?
Yep. That's probably
And
one of the reasons why Java went this way, I guess. Because I
yeah,
mean,
but why not introduce just normal coroutine and trying to bend it in some undercover?
yeah, well, I guess it's due to the backwards compatibility stuff. That's one of the reasons why Java is moving so slowly for years. Because I
Yeah,
mean, Kotlin had this stuff for years already, but yeah, it's just Java catching up, I
yeah.
guess.
I think the same way. Thank you.
I think you have coroutines in Kotlin, so we can actually use Kotlin instead. Anyway, Jakub, I'm quite puzzled, to be honest, because when I started, as I said, like 25 years ago, using threads heavily, those were supposed to be green threads, right? So kind of virtual threads. So we already had them. So then it became these became platform threads in Java, and now we have virtual threads again. You know, what's the history? Just out of curiosity.
Good question. I have no idea.
Okay. Sorry. Yeah. But you know, Java already started with the green threads, you know, so those were like virtual threads or whatever now. So I don't know if this is only like syntactic sugar or whatever.
So with million connections, do you see new bottlenecks? I don't know, like RNG generation, if you are making secure connections or logistic related to the threat management, as opposed as like previous bottlenecks which you've seen?
Yeah. Well, this is just a very first thing that you will hit because when you create an empty Spring Boot application, by default, I believe it still has Tomcat, right? And the default thread pool there is like 200 only. So if you're unlucky enough and you're the request number 201, and you'll be the one waiting. But then, yeah, that's all the operations that you do back there. At some point, you will hit the database that will just add some stuff and all these things. But that's where we usually add tracing, and we check stuff like Zipkin to see like where is the next bottleneck. Do that. So it's not really just that. It's just this allows you to have one less thing to think about because it will just work.
You still have circuit breaker, you have queues, but you move them to different place, basically, not on your application side.
Yeah, well then things get a bit complicated because all this stuff. I mean, your application can be fairly simple if you are using service mesh, for example, but then you're pushing responsibility to some other department, and it gets
Not
even
your
more
problem
complicated.
anymore. Yes, it's their
Yeah.
problem.
Guys, last question. So use this opportunity wisely.
Yeah, thanks for the talk. You mentioned you worked with Go, so what's your impression after, like, if you compare the concurrent model in Go and the one that you described right now?
Yeah, I'd say it's a bit better in Go because I mean you can write fairly simple code and the channels help a lot. There are no channels here. You need to like work around that, and it's a bit different, but it's still like Java. I would say that the biggest advantage of Java is that anyone can learn it quite quickly, and if you know how, you can crunch quite a lot of like.
Sorry, but yeah, you can say the same for Go. Basically, it's really
Oh,
simple,
yeah.
really simple language. You can like start to run some code after like finishing Go tour.
Yeah, and I mean, I really like Golang. If I started a new company right now, I would probably do the backend in Golang, personally, because I really enjoy that. But when that application gets bigger in Golang, it tends to be quite messy.
Yeah, thank you.